Hello everyone, I'm glad to present our research, Contention-Aware Mapping and Scheduling Optimization for Network-on-Chip-based Multiprocessor System on Chips. For this work, firstly, I will introduce the research motivation and make the contributions clear. Then, I will briefly discuss the problem and our proposed multi-objective evolutionary algorithm. After that, I will talk about the experiments and conclude the work. The scalable communication architecture makes network-on-chip a prevailing solution for multiprocessor system on chips. An important issue in the network-on-chip paradigm is how to map and schedule tasks of an application to processing elements. Given a task graph that represents the application, the mapping stage allocates each task to a suitable processing element, whereas the scheduling stage focuses on the sequence of tasks on one processing element. For example, we give two mapping figures with computation and communication concerns, respectively, and we show the corresponding scheduling figures for these two mappings. To make the example clear, only one task is executed on each processing element. We can see that the main span of A is 99 and B is 97. Here, two questions are raised on design space exploration. One is how to minimize communication contention. The other one is how to reduce main span and energy cost. They are also the motivations of our research. Although some related works have discussed this optimization problem, no one considered the mapping and scheduling optimization of the main span, the energy consumption, and the communication contention concurrently on heterogeneous architectures with multiple capacities. The model is closer to the actual situation, yet more difficult to solve. Since there are 22 equations for this model, here we do not list them all. The model consists of mapping constraints and scheduling constraints. The novelty of the proposed formulation is to avoid the communication contention in both spatial and temporal aspects. In spatial aspects, we propose to utilize overlapped communication paths to estimate the degree of contention such that they can be minimized in mapping state. In temporal aspect, we sequentialize data transfer with potential contention by introducing additional latency. As for complex objectives, the contention degree is evaluated by the overlapped path between two communication paths. The main span is related to computation cost and communication cost. The energy consumption includes the dynamic, static, and communication power consumption costs. To solve this challenging problem, we propose a multi-objective hybrid search algorithm. In this algorithm, we initialize some solutions with random and heuristic-based individuals. The task clustering heuristic is to group tightly coupled tasks according to their dependency relation. The capacity-constrained cluster refinement heuristic is to achieve a balanced load between various processors. The spiral mapping heuristic is to reduce the communication by considering the physical locations. In the evolutionary process, we combine genetic operators and Pareto local search to balance the exploration and exploitation of the algorithm. The epsilon dominance is used to save the computation effort. The encoding of the chromosome is shown in the top figure. The tasks are executed one after another from T1 to Tn, and we use n pointers to divide n plus 1 processors. In this way, the solution of the algorithm can be transformed into real application plans. The genetic process is also given in the figure, and we don't introduce it in detail. We further propose an indert-based Pareto local search to improve the solution that is generated by the genetic process. The local search tries to indert one random task from current solution into other positions to generate neighborhood solutions. If the objectives are updated by absolute dominance relation, the current solution is replaced by the neighborhood solution. This process continues until the times of iteration reach the maximum limit. In a word, the proposed algorithm consists of 3 heuristics, 2 genetic operators, and 1 Pareto local search with absolute dominance. We conduct 3 experiments to evaluate the quality of solutions, the flexibility in design space exploration, and the strategy verification. We use the set coverage metric and the hypervolume indicator to measure the performance of algorithms for multiple objectives. As for the flexibility experiments, we draw the figure of the Pareto front visually. The comparison with exact solving techniques involves popular tools Z3 for SMT solver, Cplex for MILP and CP solvers. We also compare our algorithm with the classical framework for multi-objective optimization called NSGA2. The benchmarks include randomly generated ones and real-world applications. Now we show the comparison results with both exact and meta-heuristic methods. As the exact solvers can only handle small-scale instances, we only list these results in the table. We can see that MOHA can achieve the same set of solutions as exact methods and performs better than NSGA2 on the first case. As for larger instances, we can see MOHA outperforms NSGA2. What's more, the local search and the initialization with multiple heuristics are effective. At last, we explore the flexibility of MOHA for solving a large-scale application with 4 network-on-chip platforms. We can conclude that the 3x3 platform may be a trade-off between parallel computation and the introduced communication cost, and could be considered as an appropriate platform for this benchmark. So let me make a conclusion. In this paper, we propose to evaluate the contention degree in terms of overlapped communication paths and regard it as an objective to be minimized. Regarding this problem, we provide a hybrid evolutionary algorithm to optimize multiple objectives for mapping and scheduling network-on-chip-based multiprocessor system on chips. The extensive experimentation demonstrates the efficiency and effectiveness of the algorithm in finding optimized solutions. That's all. Thank you.